If you feed a machine raw, unstructured instructions, computational logic breaks down. The processor cannot execute a task without a strict, unbending order of operations. Standard mathematical syntax, known as infix notation, where the operator sits between two variables, like a plus b, is designed for human readability, but for a computer, it is structurally problematic. This diagram shows the ambiguity of infix notation. Given a plus b times c, a computer cannot know whether to evaluate left to right or defer addition until multiplication completes. To resolve this, we insert parentheses and hard-code precedence tables, dictating which operators outrank others. This creates a heavy evaluation loop. A processor attempting to solve a long equation must constantly jump back and forth across the string, diving into nested parentheses and referencing external rules before it can execute a single calculation. Human mathematical syntax prioritizes visual comprehension over computational speed. The ambiguity makes it difficult to process quickly. Optimal machine computation requires stripping away that ambiguity. This is achieved using reverse Polish notation, commonly known as postfix. Postfix is a mathematical syntax where operators follow their operands rather than sitting between them. Postfix embeds the order of operations directly into a linear sequence. Variables a, b, and c are arranged first, followed by multiplication, then addition. Parentheses are eliminated. This purely linear format allows the machine to evaluate the entire expression in a single forward pass. This introduces an engineering problem. We need a fast, algorithmic way to translate nested human mathematics into this linear machine code. The tool required to bridge this gap is a specific data structure called a stack. A stack is a memory buffer that operates on a last in, first out, or LIFO principle. It acts as a temporary holding cell, storing data precisely until the algorithm determines it is ready to be processed. By scanning the input equation one character at a time and routing the operators through a LIFO stack, we generate executable postfix code. The conversion algorithm acts as a strict mechanical filter. It requires absolute routing rules to process the string. The core heuristic separates the components. Operands, the variables and numbers, bypass the filter and go directly to the final output string. Operators, like plus or minus signs, are pushed into the stack to wait their turn. This three-tiered precedence table acts as the authority. It dictates exactly when an operator is allowed to leave the stack. The rule is strict. Operators occupying a higher priority tier, like exponents, must always execute before those in a lower priority tier, like multiplication or addition. When two operators from the same precedence tier meet, the algorithm relies on a tiebreaker called associativity. This dictates the directional order in which consecutive operators of the same tier are processed. Standard operations use left-to-right associativity, meaning the first operator encountered in the string takes priority. Exponentiation is the exception. It evaluates right to left. Precedence and associativity act as the invariant logic governing exactly how the stack sorts characters during the linear scan. This workspace tracks the algorithm as it executes. We have the input string at the top, our empty LIFO stack in the center, and the resulting output array at the bottom. We scan the first token, A. Because it is an operand, it bypasses the stack and drops into the output. Next is the addition operator. The stack is empty, so the plus sign is pushed directly inside. The scanner reads B, which bypasses the stack as an operand, and joins A in the output array. We hit the multiplication operator. The algorithm compares the current operator's precedence against the operator at the top of the stack. Multiplication has higher precedence than addition. The multiplication sign is pushed into the stack, resting on top of the plus sign. The final token, C, bypasses the stack and goes straight to the output. The input string is fully scanned. The algorithm triggers its end-of-string protocol, emptying any remaining operators from the stack. Elements are removed based on LIFO principles. The topmost operator leaves first, so the multiplication sign pops to the output. Finally, the addition sign is popped. The sequence is complete. By enforcing precedence logic and LIFO removal, the stack guarantees a mathematical sequence that requires no parentheses for a machine to understand. Next, we must address explicit human overrides, like parentheses, and how the algorithm resolves precedence ties. We will use a more complex expression containing parentheses and a division operator to trace these edge cases. Fast-forwarding through the initial scans, the output contains A and B, while the stack holds the plus and multiply signs. The scanner stops at the left parenthesis. A left parenthesis acts as a temporary floor. It is unconditionally pushed into the stack, ignoring previous precedence rules. As we scan the internal expression C minus D, the stack builds on top of the parenthesis floor. C goes out, minus goes in, and D goes out. Encountering the right parenthesis triggers a pop loop to clear the local grouping. Operators pop to the output continuously until the matching left parenthesis is reached. At that point, both brackets annihilate each other and are discarded. The scanner hits a division operator. The top of the stack holds a multiplication operator. Because division is not greater than multiplication, they are considered equal. Since multiplication and division are equal and left associative, the older operator, the one already in the stack, must execute first. The algorithm must pop operators of equal or higher precedence from the stack before it can push the new operator. E goes to the output. We reach the end of the string and pop the remaining division and addition operators out of the stack to finalize the sequence. Operands go directly out. Operators wait inside the stack, and brackets strictly control the local flow of data. The systemic efficiency of this algorithm makes it a standard in computer science. This layout shows the big O notation for the algorithm. Because the scanner traverses the input string exactly once, and each character is pushed or popped a maximum of one time, it achieves guaranteed big O of n time complexity. The space complexity is also linear. The memory usage scales strictly with the number of operators stored in the stack at any given moment. This mathematical parsing logic serves as the front end for modern compilers and syntax evaluation trees. This logic provides the foundation for software interpreters and systems that must process complex data structures in real time. Mastering algorithmic state management via the stack provides the mechanism to translate human intent into executable machine reality.